So hello everyone, today we will be presenting an event-driven cloud-based file processing. Currently, many of the companies have a static-based file processing where for each vendor they have to make a separate workflow like the separate lambda and step function. So we are coming up with a dynamic approach where we have a centralized like a config-based system where for each new vendor we have to just update the configs. So we have stated three different approaches. So let's begin. So this is our approach. It is an event-driven file processing with Amazon ECS as a task. So this is the entire flow of our architecture. So the user or a vendor will upload its file in its specified folder in the S3 bucket. So then we'll have an S3 notification which will be stored in SQS. So SQS is used for storing the messages such that there can be a message loss or we can apply the retry logic. In the SQS, we have also applied the batching and the batching window is of 5 seconds. So if within a 5 seconds, we can have up to 5 files processed at once. So this SQS will then trigger the alias lambda. So that lambda will just extract the user ID from the S3 key as well as check for the idempotency as well as load the user config from the DynamoDB. As in DynamoDB, we has a user config table and then also write the audit log. The audit log will be started from here. The main purpose of lambda is this is getting the environment variables as well as starting the target task. So this is the basic configuration which we are using, and it is an on-demand process. So there will be no idle cost, only when runs when needed. In the processor container, we'll have an app.py. So it will basically download the files from the S3, extract it as well as apply the skipping rules or the renaming rules and split the larger files into a specified size, and then finally it will be uploaded into the output bucket. So this will be the entire flow, as well as we are using Amazon CloudWatch for the logs of the lambda as well as the ECS, and this is the Amazon DynamoDB tables. So basically we have three tables. One is the user config, another is the audit logging, and third is the processing state. The processing state is used for idempotency check. So if, for example, if a user uploads the same file again and the content is same, then the process will basically skip the processing of the folder. But if the file name is same and the content is different, then it will process the system. So this is all about the first approach. Let's get to the second approach. Here we are using ECS as a service. So why do we need this? So consider a case where there are terabytes of data and the number of files has increased to take, let's be 60,000 to 70,000 files processing. So if we use the ECS as a service for all the time, so it will have an boot up cost. So for that reason, we can use the ECS as a service, which will be started for 24/7. It will directly pull the SQS for the processing of the files. So this is the entire flow of the architecture. Here, similarly, the user will input the files in the S3 bucket into its respected folders. Once the file arrives, the S3 notification will be gone to the SQS. The SQS is for storing the message. As the Fargate service is running 24/7, it will always pull the SQS. So once the message arrives, the processing of the message starts. As the previous approach, we have three of the tables in our DynamoDB, and the processing state is working similarly as the previous approach. Once the message start processing, we'll start writing the audit logs, and once it's completed, we'll also updates the log. And once all of the process is completed, the file is stored in the output bucket. Here also we are using the CloudWatch for monitoring. So this is our second approach for the same problem. And now let's get to the third approach.
Let me walk you through this architecture for a TB scale file processing system built using Snowflake SPCS and AWS services. The goal of this system is to process large volumes of files up to terabytes while keeping the architecture simple, highly reliable, and extremely cost efficient. What makes this design interesting is that it combines AWS for storage messaging, Snowflake for compute, DynamoDB for faster audit logging, and most importantly, it uses auto resume pattern, reducing cost from $130 per monthly to nearly $60. At a high level, the flow is files land in S3, events go through SNS, SNS fans out to SQS and Lambda, SPCS processes the files, outputs goes best through S3, logs and audit goes to DynamoDB and CloudWatch. Everything is decoupled, scalable, and event driven. Starting from the left, vendors upload the files into the S3 input buckets. We typically separate buckets by vendor or domain like media, app, and pharma so that we can apply different processing logic and configurations. When a file is uploaded to S3, S3 triggers an event notification to an SNS topic. SNS fans out layer, which is critical here. Instead of tightly coupling S3 to a single consumer, SNS allows us to distribute the same event to multiple downstream systems. SNS lands the event to two subscribers. First, the SQS queue. This is the main processing pipeline. It acts as a buffer and ensures reliability so that no events are lost during spikes. Second, a Lambda function. This Lambda is used only for one purpose, that is to auto-resume the SPCS service. This separation is intentional because SQS handles the data flow and Lambda handles the control logic. This design keeps the system clean and scalable. The next step is the Lambda checks whether the Snowflake SPCS service is currently suspended. If it is, it resumes the service. This enables us to run the system into auto suspend mode where compute is only active when needed. This is where the major cost savings come from, reducing compute usage. Next step is SPCS pooling. Once active, the SPCS container continuously pulls the SQS queue using long polling. This ensures efficient message consumption, reduced API calls, and better cost efficiency. SPCS here acts as the core processing engine of the system. Before processing, SPCS reads configuration from Amazon DynamoDB config table. This includes vendor specific rules, file type handling, rename pattern, routing logic, and to optimize performance, this configuration is cached for 5 minutes so that we have to reduce the repeated database calls. Next step is the actual data processing which happens inside SPCS. Files are downloaded from S3, processed including splitting large files, renaming, extracting archives, then uploaded back to the output S3 bucket. The system supports parallel uploads, streaming for large files, TB scale processing. For example, 100 MB files is processed under 10 seconds. After processing, audit logs are returned to the DynamoDB. Choice is deliberated because DynamoDB provides sub 10 milliseconds writes. It is significantly faster and cheaper than using Snowflake for this purpose. Next is monitoring. Application logs are sent to CloudWatch for monitoring and debugging. This helps with the observability and operational visibility. Finally, the message is deleted from the SKS queue after successfully processing. This ensures that there is no duplicate processing, exactly one's behavior from a system perspective. One of the biggest advantages of the architecture is cost. Running SPCS 24/7 costs about $130 per month. With auto suspend enabled, it reduces the cost extremely. That's why nearly a 60 to 70% reduction in its cost is achieved without compromising scalability.
Let's start with the demo. Suppose there is a vendor Bharat and he wants to upload a file. In the DynamoDB, we have the user config known as Bharat. Here we write the JSON of the operation which we have to perform on the file. So here we are renaming the file from visualizer v2 to visualizer v1. So in the input bucket, in the vendor Bharat folder, we'll just upload the file which we want to extract. So we are now adding the file. So suppose this is the file we want to extract, we'll just upload the file. So once the file is uploaded, the message will be sent to the SQS. The SQS will then run the Lambda. Lambda is generally a trigger for our Fargate. It will also send the environment variables which it will read from the DynamoDB to the Fargate. So for the running status of Lambda, we can check it through the cloud logs. So as you can see, the today's state, so the lambda has been triggered. Now the lambda will in turn trigger the Fargate. So in the logs of Fargate, we can also see that the file has been triggered. If we click on it, we can also see the we have uploaded file, extract this file. We have also skipped some of the files as we have defined in the config. Once all the process is done, the result will be stored in the output bucket. We can see the result from the designated user folder, which is Bharat here. So we can see the model V13 which we have input has been extracted here, and all the process has been applied on it. Like rename the file from version visualizer V2 to visualizer V1. It was the renaming script which we have applied, as well as it has skipped all the .env folder which we have written in the config. So that's it for the demo.
Okay, so let's move to our demo video. First, we are going to see that all our services and compute pool is suspended. Now, what I am going to do is I'll be uploading a file to our input bucket. So I have uploaded a HTML file called AWS cost breakdown. Yeah, so after uploading file, let's see if our lambda is triggering the SPCS container. First, we'll see the CloudWatch logs. So in the CloudWatch logs, we can see that the lambda function is triggered, and it has connected to our Snowflake SPCS container services. And the procedure is successfully run. This procedure basically triggers our service and container. Now we can see our services in starting stage. So first let us see our service logs. So yeah, as we can see in these logs, it has received a file called AWS cost breakdown, and it has successfully processed the file. After processing the file, it has uploaded the file to its final destination, and all the audit logging is performed by our Snowflake procedures, which is then stored into our DynamoDB audit log tables. So this is the final output bucket which we will be going to see. Yeah, so media vendor one dev, then data. Yeah, so this is the file media vendor one AWS cost breakdown.html. So the renaming operation has been performed, and we can see. Let me walk you through exactly what we are paying in each option and why the numbers are what they are. The single biggest expense in every option is compute. This is what we pay for the actual processing power in running our pipeline. In the ECS Lambda option, Fargate compute costs $43.40 a month. That's because containers only spin up when a Lambda function triggers them. So we are not paying for idle time. In the ECS pooling options, that jumps to $83.90. The reason is simple. The container is always running, always checking for new work. So we are paying for 24 by 7 uptime even when there is nothing to process. On the Snowflake side, SPCS with also suspend compute down to somewhere around $35 to $50. It works similarly to Lambda model. When there is no activity, the container suspends and we stop getting charged. SPCS running 24 by 7 is the most expensive at $140 for compute alone, nearly 3 times the Lambda option, purely because it never sleeps. S3 storage is $20.70 a month across all four options. This doesn't change regardless of which architecture we pick, because we are storing the same amount of data either way. Think of this as a fixed base cost. S3 requests and data transfers. This is where Snowflake options carry an extra cost that ECS doesn't. Every time our pipeline reads or writes a file on S3, a get or put request, Snowflake gets charged it separately. That adds roughly $5 to $10 a month. On top of that, moving data between Snowflake and S3 incurs a data transfer fees anywhere from $0 to $6 depending on how much data is flowing. The ECS option does not show these charges because they are likely to be bundled into the Fargate egress cost, but they aren't broken out explicitly. Third is messaging, SQS, SNS, and Lambda. These are the cost for the event plumbing, the queues, and the notifications that tell our pipeline when new data arrives. SQS cost 0.03 on the ECS side and 0.5 on the SPCS side. The difference is because Snowflake setup needs slightly more messaging infrastructure to bridge AWS events into Snowflake. SNS, this notification service, is only used in SPCS setup at $0.1 a month. ECS handles this differently, so there is no SNS cost there. Lambda is effectively free across all options. We are well within the free tier, so it shows $0 on ECS and just $0.2 on SPCS. Monitoring. DynaDB and CloudWatch. These are our audit and observability costs. They are small and consistent across all options. DynaDB is used for audit logging and costs about $1 across the board. CloudWatch handles our logs and metrics at $1.5 on all the four options. These costs doesn't really change with architecture choice. They are just cost of being able to see what our pipeline is doing. So when you add it all up, ECS Lambda comes to $55 to $60 a month, cheapest because compute is low and there are no extra S3 request charges. ECS pooling comes to $100 to $105, almost double, purely because the compute never switches off. SPCS auto suspend lands between $65 to $90. Competitive with ECS Lambda, but with some variability from those S3 requests and data transfer cost. SPCS 24/7 is $153 flat, the most expensive because you are paying for always on compute plus the additional Snowflake specific charges. So the cost story is really about one thing. How much are we paying for compute even when nothing is happening? The event driven options, ECS Lambda and SPCS auto suspend, win on cost because they never stop the meter when they are idle. The always on option cost more but give you instant readiness at all times. Everything else, storage, messaging, monitoring, is roughly the same across all the four. In our next version, our main focus will be our monitoring and observability on the user's end. Thank you.